Hello, Chemistry 30, and welcome to your lesson on Bronsted-Lowry acids and bases. We're going to get into a new theory of acids and bases than what you learned in the past. Right now from Chemistry 20, you are on the modified Arrhenius theory, which is that an acid is something that reacts with water to make hydronium, while a base dissociates or reacts with water to make hydroxide. We're going with a new definition of acids and bases today, so we're kind of going the next step in our understanding of the theory of acids and bases. So today's objectives is to describe Bronsted-Lowry acids as proton donors and bases as proton acceptors, and to identify conjugate pairs and amphiprotic substances. So really the answer of what we're doing is right there, and that a Bronsted-Lowry acid is what we call a proton donor and a base is a proton acceptor, but we're going to get into it and get more in detail. So the background of this is scientists found that some substances acted as acids or bases when they were not in a water solution. The previous definition of an acid reacts with water to make hydronium means that water has to be present. But they found that things could act as acids or bases even without water being present, so it not being within a water solution. So in science, when evidence is found that doesn't agree with the theory has to be scrapped or changed. That's the beauty of science. Okay, when new evidence is found to prove something false, well then the scientific process means that the theory then is no longer accurate and we have to come up with a new theory. So whenever we talk about theories in science, what we're saying is it's something that essentially all the evidence so far has agreed with. So we have no evidence that doesn't agree with that theory when we're talking about theories that are still universally accepted in science or that are accepted in science. So Bronsted-Lowry basically was around them finding that some substances again acted as acids or bases even without water present. So as a result, we had to define acids and bases differently and go through a different theory. So that was Bronsted-Lowry that came up with the acid and base theory that actually we use all throughout chemistry today. So this is it. This is the end of your acid and base theory journey that you've been taking throughout high school, from Arrhenius to modified Arrhenius to Bronsted-Lowry. So for an acid, and we'll write this out here, an acid is a proton, oh, this is messy, is a proton donor. So what is a proton? Well, a proton is a hydrogen ion. It's an H positive ion, right? Because hydrogen is one proton and one electron. If I get rid of the electron for hydrogen ion, all I'm really talking about is a proton. So you can treat this as it is a H positive donor. So it gives it up. It releases it, however you want to say it. It's losing a proton when we talk about an acid. Well, if we talk about a base is a proton acceptor. So it is taking a proton on. It gains a proton, and that's what a base is. Now, you might be thinking right now that a lot of this terminology is familiar, right? It gains, it loses. Well, that's because when you think about redox chemistry, it's electrons that are transferring. And then in acid and base chemistry, it's protons that are transferring. So actually our work in redox and our work in Bronsted-Lowry acids and bases are very similar. Okay, they're not super different. So a base is again a proton acceptor. It gains a proton, and proton is an H positive ion. So if we take a look at two examples, let's try to figure out what the acid is and what the base is. So if I look at HCl and NH3, and then it turns into NH4 positive and Cl minus, well, you can see that the H, right, moved from HCl to NH3. So this H went from here to here. So that would make HCl the proton donor. In other words, this is the acid. Well, NH3 being the thing that accepted the proton acceptor, this is the base. Okay, so acid for HCl and base for NH3 that accepted the proton. What about in the second reaction? What is the acid and what is the base? Well, you can see that H goes from H2CO3 to H2O. So this is the acid. It donates a proton, while H2O ends up being the base. It accepts a proton, and I end up with H3O positive and HCO3 minus. Okay, what's interesting about this is that water, as you saw here, was acting as a base. If I take a look at this reaction, water actually is acting as an acid, because in this reaction, water ends up losing a proton and it gives it to NH3, right? This is where the proton is moving, making water an acid and making NH3 a base. So water is interesting that it can act as either an acid or a base. So here it is an acid, but it can also be a base. You might remember that in redox, water could be an OA, an oxidizing agent, or a reducing agent. Kind of similar here. Water can be an acid or it can be a base. Is it a weak acid? Yeah. Is it a weak base? Yes, of course. But it can act as both. We call this amphiprotic, which is a term we'll talk about in a little bit. So this is kind of an interesting question. Is NaOH aqueous a base? Well, kind of no. NaOH itself is not a base, but when I dissociate this into Na positive aqueous and OH minus aqueous, OH minus is the base. So this is the thing that can be a proton acceptor. Is NaOH aqueous a basic solution? Yeah, of course it is. And that's because it has the hydroxide ion in it. So we got to be really specific when we're talking about what the acid or the base is. And again, like always, whenever we have an ionic compound, we need to dissociate into the two ions before we analyze how it is as an acid or a base, again, if it's ionic. So amphiprotic things can act as an acid, so a proton donor, or a base, so a proton acceptor. So it can be both. It can be an acid or a base for amphiprotic. So now let's talk about the conjugate acid and base pair. So for identifying the acid and base, we were looking at the reactants only. Now we're going to look at the products, right? Because in an equilibrium reaction, products are constantly turning into reactants. We have the reverse reaction as well as the forward reaction always occurring. We're going to look at both. So the conjugate acid or base is essentially the product, and it would be what we're looking at for the reverse reaction. Okay, so conjugates are products, and are the acids and bases for the reverse reaction. So let's take a look at the example above, because I think that's good to look at. If I take a look at CH3COOH and H2O, this right here is the acid because it gives an H to H2O, which is my base. Okay, but if I look at the reverse reaction, here I have hydronium, an acetate ion, and here the hydrogen is being given to the acetate ion to make the reactants I have. So that would make this my conjugate acid, and it would make the acetate ion my conjugate base. Okay, so I have my acid and my base, and I have my conjugate base and my conjugate acid. If I put these together, this is a conjugate acid-base pair. I have an acid, and then I have its conjugate base. You might notice that these differ by one H positive, one proton. Okay, again, here I have my base and my conjugate acid. So together, these make a conjugate acid-base pair that differs by one proton. That definition is very, very important. So a conjugate acid-base pair differs by one proton, which again is an H positive. Look at that, it's a pair of pairs. Isn't that fun? So if I take a look at my data booklet, I'm gonna have to skip ahead a few slides here to show you this. But if I look at my data booklet, oh, wait for it. Oh, yeah, no, it's way ahead. Okay, bear with me here. Bear with me, because it's in another lesson entirely. This data table in your data booklet has acids and conjugate bases. So these are conjugate acid-base pairs, right? So I have my acid formula and then I have the base formula. And for each one of these rows, the two things differ by 1 proton. So this is a table of conjugate acids and bases, right? Of conjugate acid-base pairs. So this table we're going to be using a bunch later on, but for right now we're just focusing on the definitions of acid and base, conjugate acid, conjugate base. Okay, back to where we were. So if I take a look at HF aqueous, H2O making F minus and H3O positive, here's my acid HF, my conjugate base is F minus because it lost a proton from here to here, and then I have H2O liquid, which is acting as my base in this scenario, right, because it accepts the proton to become hydronium, which makes hydronium my conjugate acid. So that's kind of how this works, and this is actually really kind of nice and easy. I feel like this concept is a nice break because it's really easy to see the acids and the bases and then the conjugate acid-base pairs. So here's another question. Take a moment, see if you can label the acid, the base, the conjugate acid, the conjugate base, and then kind of draw a line to connect the two pairs. Okay, so to connect the conjugate acids and bases. So looking at this, H2S gives a proton to CO3 2-. So this is my acid, and this will be my base because it accepts the proton. If I look at the reverse, right, this hydrogen is being given to HS-, so that makes this my conjugate acid, and this is my conjugate base. So now I'm going to connect the two things that differ by a proton. So H2S and HS-, this is a conjugate acid-base pair, and CO3 2- and HCO3-, this is a conjugate acid-base pair. So these are my two conjugate acid-base pairs between this and this, and this and this. All right, the stronger the acid, the weaker the conjugate base. And the stronger the base, the weaker the conjugate acid. This might remind you of the stronger oxidizing agent you have, the weaker the Ra is on the other side. This is the same kind of deal. The stronger the Ra, the weaker the SOA is on the other side of the half reaction. So just kind of looking through this H2S, it's a weak acid, but it's a pretty good weak acid, right? So this, being a pretty good weak acid, means that HS- is a really bad, super weak base. Okay, so because this is a relatively strong acid for weak acids, this is going to be a very, very poor base. When I take a look at a strong acid, something like HCl, right, which right away when it goes into water, it just forms hydronium, but that's a later lesson. Cl-, it isn't even a base. It's so bad as a base, it doesn't even act as a base at all. It's just not a base. Anything above hydronium on the line, we actually just, the conjugate base for those acids, they don't do anything at all. They do not act as a base whatsoever. All right, so this concept allows strengths of different acids and bases to be compared to predict the equilibrium position. We're going to be doing a lot of this over time. Here's another question where we're going to label the acid, the base, the conjugate acid, and the conjugate base. So try it out, see if you can label it, and then also label the pairs by drawing lines to show them. So HClO4-, this is going to be my acid because it is giving a proton to water. That makes water a base as a proton acceptor. If I look at my products, I have hydronium here being a conjugate acid, and ClO4- is going to be a conjugate base. Now this is a strong acid, which means that this is a horrible, horrible base. So for my acid-base pairs, I have this as a conjugate acid-base pair, which differs by 1 hydrogen ion, 1 proton, and this is a conjugate acid-base pair. One other one. So CH3COOH, this is going to be my acid. It gives a hydrogen to water, so that's going to be my base as a proton acceptor, which means that when I look at hydronium, this is going to be my conjugate acid, and acetate ion will be my conjugate base. So I have this as a conjugate acid-base pair, and I have this as a conjugate acid-base pair. And again, by definition, that means that it differs by 1 hydrogen ion, 1 proton, and that's it. Kind of an interesting one here, looking at phenolphthalein as an indicator to see what it would be. So phenolphthalein has the short form of pH minus. The actual formula for phenolphthalein is incredibly complex. It's a crazy molecule if you look it up. Tons and tons and tons of carbons and rings involved in that. But anyways, if I look at this, HCl would be my acid, which makes pH minus my base. And then as a result, that means that Cl minus would be my conjugate base, and HPH would be my conjugate acid. So this is a conjugate acid-base pair, and this is a conjugate acid-base pair. For the indicator, pH minus as this color would actually end up being a pink color, right? The base form of phenolphthalein. While the HPH color for phenolphthalein, this is the colorless color. Okay, so this is the color that it is. My son is trying to sneak behind me. So this is the color that it is when it is in with a acid, right? Because I form a lot of this product right here. All right, that's it for today.